I would suggest you are using you're staying here because otherwise the recording will not
Okay.
be.
Okay. All right. Thank you, Chair, and good morning, everyone. My name is Fei Dai, currently Assistant Professor of Construction Engineering at the Department of Civil and Environmental Engineering in West Virginia University. The topic I'm going to present today is comparing feature matching algorithm for measuring in-plane strengths on civil infrastructures. Here we focused on 2D scope instead of 3D. And actually, the work was done by my graduate students. The first author, Yo Yifan, now he has graduated and left for another school, so I'm here to help him to present. And of course, this work is assisted by another author, Jia Qing Zhao from Tsinghua University. Well, there's no need to argue that civil infrastructure is very critical for our daily lives. However, they are aging and become more vulnerable. And the American Society of Civil Engineers, yearly ranked the civil infrastructures very low. For example, the layer grade is only like C and D, the highest is 1. And now the safety integrity of the infrastructure may become a very important topic due to the public concern. And once the infrastructure fails, you can imagine the consequences are very severe. And here are a couple of examples we could see here that took place in the United States. So we could see, whenever a collapse of overpasses, bridges, tunnels, they are always accompanied with injuries and deaths. So it's very important that we come up with reliable solutions to timely monitor the integrity of our infrastructure to guarantee the level of services. Well, in the field of communication and surveying, the photogrammetry, the fundamental of 3D reconstruction, the spatial data collection has become mature. And of course, they're still facing challenges such as the level of accuracy, how to increase the accuracy, that to meet the needs of the real civil engineering applications. Other challenge includes the level of automation, but still the technologies in those fields presents opportunities for us to look at technology development to address the problem we face. So here the specific scenario is, what if the information could be captured, measured on the civil infrastructure that can reflect the performance of those structures. Here, we're particularly focused on the visual sensing, that is an image-based technology. And of course, in the literature and in practice, there are some other methods being explored and ongoing. There are two classes of technologies methods being explored. The first one is contact measuring methods, the wide and wireless sensor networks, for example, the optical fiber sensors. And of course, they have benefit that very good accuracy and low cost once installed. Either embedded or on surface of the structure. Can continuously collect data and monitor the performance of the structures. But there are also downside of the technologies. That is, the manual installation work needed and the depth rate of the sensors is high. And I think this cannot obtain the full field measurements. The full field measurement here is give the field of view, and a method could generate the map of the deflections or strengths. And now technologies, GPS-based method. Of course, GPS itself it's a remote, but there's needs to install the receivers on the structure. That's why we put it here to conduct measuring methods. and it's been used to monitor some of the infrastructures. But again, I mean, there's needs for manual installation, and also cannot obtain the full field measurements. Normally, I mean, we only look at some of the reference locations. A second class of method technologies are non-contact measurement methods. The first one is laser scanning, and the majority of you are very familiar with this technology. Basically, it generates dense point cloud that's very accurate, and measurement could be taken on top of it. And the very high accuracy is benefit of it. And of course, the downside is the equipment is bulky, and to our knowledge, the equipment is expensive. The second one is the total station surveying methods. Operation is very easy, convenient, very familiar by the industry, but the downside is that we can only measure one point at a time. And also, we cannot perform the full field measurements, and moving the equipment from location to location is not a very job. The last one actually is in civil engineering field is emerging. We would call it visual sensing based methods. That is using the image being captured by visual sensors, and then we try to perform measurements on top of the images or video frames being collected. In terms of cost, it's lower, and it could perform full field measurements, but still there are challenges. We will call downside here is the accuracy is not very certain, and also the level of automation still needs more exploration. So how the visual sensing based method work to measure deflection of structures? The principle is triangulation. So basically, we try to identify and match the corresponding points across different images before deformation, after deformation, over time, and then we try to measure discrepancy and then reproject the discrepancy into a 3D space. Now here, of course, we're focused on the accuracy. It is key. Otherwise, that doesn't make any sense. So the key is how accurate, how good the corresponding points are detected and matched, because it have a very significant impact on the resulting accuracy of the deflections. And in the literature, actually, in the computer vision field, in civil engineering field, there are already studies, compare different feature identification and matching algorithms, the sit and the surf, and being explored and reviewed that it generated the highest performance in terms of accuracy. On the other hand, in the manufacturing field, the digital image correlation being widely used, and also it's proven technology, the accuracy is satisfactory. But here, still unknown. Well, in terms of comparison between these two set of algorithms, two set of technologies, which one performs better? So the objective of this study is to perform the comparison, try to measure the level of accuracy among these algorithms, and after that we select the one that performs best, and then validate the visual sensing based method to see eventually the deflection and strain and how good they are. With this objectives in mind, so we designed the experiment. Actually, the student did, and the hardware that we used is the industrial camera, and it's Meta G. It's a commercial available industrial camera. The good part about the industrial camera is the distortion. Distortion of the lens is minimized. there's no need to perform calibration, and also the quality of the image is as good. Okay, we used the concrete compression machine that's in the concrete lab back in West Virginia University. The purpose of it is to generate the ground truth data. We do the displacement and then we measure it. We benchmark with some of the data collected by other devices. See how accurate the video sensing based methods are. Okay, the experiment are divided into two parts. The first one is comparison among these three type of algorithms. Well, it's very simple. So we use the industrial camera to capture images. So here the first row actually is one group of experiment. The second row is another group of experiment. The first row actually we intentionally hoist the piece of wood by 2 millimeters each time. We take pictures, and this way we know the ground truth, and then we use the image-based algorithm to measure the deflection, do the comparison. Here the ground truth data actually is recorded by the concrete compression machine in the structural lab, and we can very accurately control the distance it travels. There's a meter to record the traveling distances, and we use that as the ground truth data. Well, I'll skip the detailed implementation, and here I want to show some of the experimental results. Here for the accuracy, you could see actually the DRC, the digital image correlation, performed best. Generally speaking, and also this was concurred by second group of study. Again, we'll see the DRC algorithm performed best in terms of accuracy. And the second one is surf, and the worst one is the seat. Okay, that means the previous two result actually the errors measured in terms of pixels, and then we based on the parameter of the cameras, we can convert it into a metric units, that is in terms of millimeter. And then we can also do some prediction to see how the parameter of the distances can impact the accuracy. Here, this slide shows the results. We could see again the surf performs best, and again we could see within the shooting distance 10 meters. Actually, the DRC algorithm can generate the accuracy within 0.5 millimeter, and as the distance goes further, and obviously the accuracy will go down. And within 30 meters, still the DRC algorithm resulting the accuracy level between 0.5 and 1 millimeter. So general conclusion is the DRC algorithm performed the best in terms of accuracy. Having this conclusion, and then we implemented the pipeline, and then we do another set of experiment in the structure in the concrete lab. Here is one snapshot of where we're doing experiment, and another technician helped us to collect the data. And here, actual force was applied to a cylinder concrete, and we used the linear variable differential transformer to collect the deflection of the concrete, and we use it as the ground truth data to compare the measurement generated by our algorithm. And here are some of the pictures. It looks very identical because the deformation is very small. And also we use some of the well-established equations to generate string map. Here we could see on the on the up right corner, the red one indicates the string. The string is large. And also on the bottom right corner, the string is large. And this slide shows the numerical comparison in terms of deflection and the string. Over here, we could see, in terms of deflection measurements, this technology, is unsatisfactory. The accuracy can be up to 99%. But we have to confess, okay, in terms of the string generation, only the accuracy is only about 88%. Still there's room for improvement. Okay, I'm going to stop here and some of the conclusions. So we have performed some experiments to review the how accurate the visual sensing based method can obtain. And based on our experimental results, actually the digital image correlation performs best. And there are also works need to be done in the future. One, for example, we didn't present here. Actually, the processing time of DIC is slower than SURF and SIG algorithm. So there need to find ways to boost boost the computational time for image correlation algorithm. And the second one is how to project the in-plane constraint deflection onto the 3D space to generate out of plane deflection string measurements. Okay, the work is still ongoing. Here, the hardware configuration have been done. Actually, the outlet image shows the stereo rig. Also, we use synchronization devices to synchronize the image frames to make sure the frames being processed are obtained at the same point in time. And the right side of the slide actually is a framework that we're implementing right now. With that, I'm going to conclude my presentation and welcome any questions. Thank you.